Think about the first 20 minutes of your day. Before you even sit down for breakfast, you've likely executed dozens of complex physics interactions. Look at this hand pulling open a heavy door. You have to exert physical effort to move that mass out of your way. Or watch this shoe pressing down on a bicycle pedal to start a ride. Pushing that machinery forward requires your muscles to actively drive it. Notice these fingers squeezing a toothpaste tube, forcing the paste out. You have to firmly compress the plastic to get the paste onto your brush. Every single one of these mundane morning actions requires you to physically interact with an object to create a change in its state. In science, we call that interaction a force. A force is simply a push or a pull that changes an object's state of motion or its position. And because all the examples we just looked at require direct physical touch to transfer energy, we categorize them specifically as contact forces. The rule for a contact force is strict. If your fingers never actually compress that toothpaste tube, the paste inside sits perfectly motionless. But this raises an interesting question. What happens when an object is forced to move, but absolutely nothing is physically touching it? While contact forces govern the obvious interactions in our lives, we are surrounded by invisible mechanisms capable of pushing and pulling without ever building a single physical bridge. Watch this pen resting on a desk. It slowly rolls off the flat edge and falls straight down. We take this for granted, but think about the mechanics of that fall. The floor didn't reach up and grab the pen. Here we see a diagram representing what's actually happening. This is gravitational force. It is a phenomenon where the Earth pulls objects toward its center across empty space. Gravity provides our first concrete proof that the strict rule of contact forces has massive planetary scale exceptions. It demonstrates that two things don't need to physically touch for one to dictate the motion of the other. In this video, a blown-up balloon hovers above tiny bits of paper, and the paper spontaneously flies upward to stick to the rubber. When the balloon was rubbed earlier, it picked up an electrostatic charge. That means it accumulated an imbalance of electric charge on its surface. That charge creates an electrostatic force. It pulls the paper upward, temporarily defeating gravity, all without a single touch. We see a similar effect if we float two magnetized sewing needles side by side in a bowl of water. Take a look at this diagram. A magnetic force causes the two needle ends to violently push away from each other before they ever make physical contact. The specific mechanics of magnetic repulsion dictate that like poles, say two north ends, will repel across a gap. Gravity, electrostatic force, and magnetic force all belong to a single scientific category. We call them forces at a distance, or more commonly, field forces. If we map out our morning routine, we can divide these interactions into two distinct columns. On one side, we have our contact forces, pulling the heavy door, pushing the bike pedal, squeezing the toothpaste. On the other side, we have our field forces, the pen falling to the floor, the paper jumping to the balloon, the needles repelling in the water. The line separating these columns comes down to one thing: the presence, or the complete absence, of a physical bridge between the actor and the object. Yet despite their radically different mechanics, both categories achieve the exact same result. They generate a push or a pull that forces the world to change. There's an ultimate irony to all of this. Human beings, and the cameras we build, can never actually see a force itself. This portrait of Albert Einstein reminds us of the reality of physics. The greatest minds in history had to map out these fundamental laws entirely by measuring the precise patterns of motion we can observe in nature. We only ever see the door swinging, the paper jumping, or the pen hitting the floor. We merely witness the aftermath of the invisible interaction. While some changes in the universe require you to roll up your sleeves and make contact, the existence of field forces proves we are part of a universe where change can happen across empty space.